This is Chapter 18 of Astronomy 100, dealing with dark matter, dark energy, and the fate of the universe. This is probably the most abstract part of the course, where we're talking about different forms of matter and energy that we really can't provide a theory for 100%. We have evidence for these things, but we have no direct proof. And so some of the things that we're talking about in this chapter are highly debatable. And we're at the sort of the edge of our base of knowledge dealing with the universe and how it behaves. And of course, the last part of the chapter deals with what's the ultimate end of our universe. So what do we mean by dark matter and dark energy? Well, dark matter is an undetected form of mass that emits no light, but whose existence explains missing mass, as we'll see later on. Dark energy is an unknown form of energy. It seems to be causing the expansion of the universe to accelerate. So we have these two things which are somewhat unknown, somewhat unprovable, but helps to explain what we observe. So here's the content of the universe. It comes down to normal matter being less than or equal to about 5% of what we have out there. Normal matter is inside the stars, and normal matter outside is 4.5. Dark matter, on the other hand, might be as high as 27% of our universe, and dark energy 68%. So it makes sense that we should be able to detect these things, right? Now we'll see. So what do we mean? Well, dark matter is the name given to unseen mass whose gravity governs the motions of stars and gas clouds. And dark energy is the name given to whatever might be causing the expansion of the universe to accelerate. So what's the evidence for dark matter in galaxies? Well, as you can see, we have a graph here of orbital velocity versus distance from the center of that galaxy. And there appears to be 4 different galaxies here that have been identified. And of course, going out from the center of the galaxy, the orbital velocity increases very quickly. But at some point, say between 50 and 100,000 light years out, the speed of rotation of that galaxy seems to stabilize or even out. So depending on the galaxy, it might be 200 or even 300,000 kilometers per second, but they are definitely moving at a constant speed after that distance from the center, which doesn't make a lot of sense, except to have something like dark matter account for it. So the mass in the Milky Way galaxy is spread out over a larger region than the stars, apparently. Most of the Milky Way's mass seems to be dark matter. And we conclude that by the fact that we have so many stars, and yet the motion of those stars around a center, which might be a supermassive black hole, varies depending on the distance from the center, except at a certain distance, then it remains constant. So the mass within the Sun's orbit appears to be 1 times 10 to the 11th solar masses, and the total mass seems to be about 10 to the 12th solar masses. So the difference between the two is at least 10 times. So something else must be making up that difference. Well, the visible portion of a galaxy lies deep in the heart of a large halo of dark matter. At least that's what we think. The spiral galaxies all tend to have orbital velocities that remain constant at large radii, indicating a large amount of dark matter. So as I mentioned before, somewhere around 50 to 100,000 light years out, that velocity remains fairly constant. So here's what we think is happening. The broadening of spectral lines in elliptical galaxies tells us how fast the stars are orbiting. So these galaxies also have dark matter. So maybe it doesn't matter which type of galaxy it is, they all contain dark matter of some sort. So what's the evidence for dark matter in clusters of galaxies? We can measure the velocities of galaxies in a cluster from their Doppler shifts. We know that galaxies are in most cases receding, so we get a red shift in their Doppler. The mass we find from the galaxy motions in a cluster is about 50 times larger than the mass in the stars. So there must be something more to a galaxy than just the mass of the stars. Clusters contain large amounts of X-ray emitting hot gas, and the temperature of those hot gases tells us the cluster's mass. So in this particular case, or as an average, 2% might actually be in stars, 13% might consist of the hot gas, but 85% of a cluster would still be dark matter. So here's a way we can detect, or think we can detect, a cluster's mass. It's called gravitational lensing, where the bending of light rays by gravity gives us a clue as to how massive the cluster is. All these different methods of measuring cluster mass indicate similar amounts of dark matter. In other words, we come up with a fairly consistent number as far as what the mass of the stars would be compared to the mass of the rest of it, which apparently is dark matter. So, these are the different kinds of dark matter evidence. Measuring the velocity of a cluster galaxy, measuring the temperature of the gas, and measuring these distorted images due to gravitational lensing of background galaxies. So, does dark matter really exist? Well, dark matter seems to exist, and we're observing the effects of gravitational attraction. But something may also be wrong with our understanding of gravity. Maybe there are exceptions to what gravity can do, and maybe matter is not the only cause for gravitational attraction. The bullet cluster, a collision of two smaller clusters, provides some evidence for the existence of dark matter. Here the blue color represents the bulk of the cluster mass, while the pink represents the gas, which is the visible matter. So we think this cluster may actually be a combination of visible matter and dark matter. So what might dark matter be made of? Well, there's two basic options. One is that it's ordinary matter that's invisible, too cold for us to really detect by any other means. Or something called a WIMP, which are exotic particles, and the acronym WIMP stands for Weak Interacting Massive Particles. So these might be mysterious neutrino-like particles. Compact star-like objects occasionally make other stars brighter through lensing, but there's not enough lensing events to explain all the dark matter. So maybe there's something else going on here. WIMPs might be the other component of this solution. So why WIMPs? Well, there's not enough ordinary matter. WIMPs could be left over from the Big Bang, and models involving WIMPs explain how galaxy formation works. So this other particle called a WIMP may be an additional particle making up the remaining matter within a galaxy or a cluster of galaxies. So what's the evidence for dark matter? Well, orbital velocities within galaxies are pretty constant at large distances. And what's the evidence for dark matter in clusters? Well, they're measured from galaxy motion, temperature of hot gas, and gravitational lensing. Does dark matter really exist? Well, either dark matter exists or our understanding of our gravity must be revised. And what might dark matter be made of? Most astronomers think that dark matter is made of particles that have not yet been discovered. So we have this very mysterious thing called dark matter that we're really not sure of. We have evidence for something like it, but we don't have proof. So what's the role of dark matter in galaxy formation? Well, the gravity of dark matter is what caused protogalactic clouds to contract early in time. So in other words, the dark matter, of which there was quite a bit in and around a protogalactic cloud, really was the cause for the contraction of the cloud into a star, or possibly a galaxy. Maps of the galaxy positions, of which we have kind of a blown-up view here going from left to right, reveals extremely large structures in the galaxies. We call them superclusters. And of course, the absence of superclusters are called voids. So structures in galaxy maps look very similar to the ones found in models in which dark matter is actually a WIMP. So as you can see, the difference between the two is very, very small. Unless our model's wrong or we've determined that WIMPs are just not the right type of particle, we are going with this hypothesis that WIMPs may be what dark matter may actually contain. So what's the role of dark matter? Well, dark matter seems to be what draws gas together into protogalactic clouds, eventually galaxies. And what are the largest structures in the universe? They appear to be distributed in huge chains and sheets, and those surround great voids, great empty spaces between galaxies. Let's look at dark energy and the fate of the universe. What's the evidence for an accelerating expansion of the universe? And why is flat geometry evidence for dark energy? And what's the fate of the universe? Well, these are different ways in which we might consider what will happen to our universe. Well, starting from the left, going to the right, we have the possibility of our universe stopping and then contracting again. That's called a recollapsing universe. The second one is what's called a critical universe, which is where the universe continues expanding, but at a set pace. And then we have a coasting universe, which is very similar to a critical universe, but expanding at a slightly higher rate. And finally, an accelerating universe, where the longer time progresses, the faster the universe will expand. So the fate of the universe depends on the amount of dark matter we think. A collapsing universe or a recollapsing universe would have lots of dark matter. A critical universe and a coasting universe would have very slight differences in the density of dark matter. And this would be an amount of matter around 25% of critical density, suggesting fate is eternal expansion. So not having enough dark matter would allow the universe to continue to expand. But what we see in the universe as far as expansion is that it's speeding up. So is it possibly dark energy? In other words, there's not enough dark matter to hold things together. Instead, dark energy is producing the acceleration. The estimated age depends on both dark matter and dark energy, apparently. So we have these two things, dark matter and dark energy, which we don't know exist for sure, but explains a lot of the features that we see in our universe and may in fact be responsible for an accelerating universe. This is something kind of interesting. The brightness of a distant white dwarf supernovae tells us how much the universe has expanded since they exploded. And if we plot those supernova expansions on a graph, as you see here, we have the average distance between galaxies on the vertical axis, and then time on the horizontal axis. 0 is somewhere just a little right of center. We see that most of the galaxies are resting on what we think might be the accelerating curve. This is the same graph you see on page 477 of your book. So we expect the universe will continue expanding forever as dark energy continues to accelerate the expansion. So based on evidence we have so far, we think the expansion will be the actual result of acceleration, not of coasting or of a critical or recollapsing universe, but an accelerating universe. So what's the evidence for accelerating expansion? Well, an accelerating universe is the best explanation for distances we measure when using white dwarf supernovae as standard candles. In other words, we know the distances to those. And what is the fate? It seems that the universe will forever expand, and in fact will accelerate as it expands.